Now we continue with linear response theory, and then at this time we will study the Schrödinger matrix. It's quite important formalism before we actually go into deriving the cubic formula, and we will start in blue. So then we write the Schrödinger equation in the interaction picture. So IH bar time derivative of state phi of t equals to perturbation in the interaction picture acting on state phi of t. Okay, so then now one can write a solution to this expression in the following way. So we can say that phi of t is equal to phi at minus infinity plus 1 over I h bar times the integral from minus infinity to t of w sub I of tau times the state phi of tau d tau. Now there's a problem with this solution, and is that we actually don't know exactly who phi of tau is, do we? So then so what we have to do is, from the knowledge of the state, now in red, from the knowledge of this state at minus infinity, which we should know at minus infinity is just a time where there's no perturbation and everything is nice and shiny. So or the state at t to minus infinity, so we can construct approximate solutions of the form phi of t to the power of n, where n is the degree of approximation. Okay, this is the degree of approximation, and the approximation is to a given order, and this can be constructed of course, where what is meant by order is the number of times the perturbation w sub I of t is multiplied by itself at different times, or evaluated at different times. Now the zero order approximation in this case, so to zero order we will consider that the approximation is equal to just this phi of minus infinity. Okay, this is to zero order. Now what happens to first order? So to first order we just replace what we have to zero order here, and we construct from there. So then to first order, phi of t is equal to phi of minus infinity plus 1 over I h bar, the integral from minus infinity to t, w sub I of tau d tau, this multiplied times phi of t to zero order. Okay, and what is phi of t to zero order? So phi of t to zero order is just phi of minus infinity, so then we write 1 plus 1 over I h bar, the integral from minus infinity to t w sub I of tau d tau, all of it acted on phi of minus infinity. Okay, so we have constructed the first order contribution, the first order correction to quantum state phi of t. Now what happens to second order? So to second order, what I just want to do is to replace in this expression here, in the solution, in the exact solution that we have for state phi of t. So instead of phi of tau here, what we're going to do is that we're going to replace now the first order correction, but evaluated at t, and we will see what happens. Okay, so then the first order correction, now the second order correction to this quantum state, so it will be given by phi of minus infinity plus 1 over I h bar. Okay, integral from minus infinity to t w sub I of tau d tau times phi of t corrected to first order. And what is this? So let's scroll down a little bit. So this is nothing but phi of minus infinity plus 1 over I h bar, integral from minus infinity to t, w sub I of tau d tau, and what we have here. So what we have here is the first order correction, which is 1 plus 1 over I h bar, integral from minus infinity to t. Now we change integration variable, so w sub I of t prime dt prime. Okay, and all of this is acting upon phi of minus infinity. Now let's see what can we do here. So what can we do here is just expand everything, and this is equal to phi of minus infinity plus this 1 times this is just itself, so 1 over I h bar, integral from minus infinity to t, w sub I of tau d tau, all of that acting on phi of minus infinity. And the second term here, the second multiplication, so we just pick up a double integral here, which is plus 1 over I h bar, a square minus infinity to t of d tau from minus infinity to tau of dt prime. Okay, and then so we have here this product of the following form. So dt prime goes after, so we have w sub I of tau, w sub I of tau prime, acting on phi of minus infinity. So if I just factorize here phi of minus infinity, I just get 1 plus 1 over I h bar, integral from minus infinity to t w sub I of tau d tau, plus 1 over I h bar square minus infinity to t d tau, integral of minus infinity to tau dt prime, w sub I of tau, w sub I of tau prime. All of it is acting upon the state phi at minus infinity. Okay, and then in a previous video, in the previous video prior to this video in linear response theory, we demonstrated that this very last term can be expressed as 1 over 2 I h bar square, integral from minus infinity to t d tau, integral from minus infinity to tau to t as well, d tau prime, time order product of w sub I of tau, w sub I of tau prime. Okay, so then this second order correction reads in that way. So it's 1 plus 1 over I h bar, integral from minus infinity to t w sub I of tau d tau, plus 1 over 2 I h bar square, integral from minus infinity to t d tau, integral from minus infinity to t d tau prime, time order product of w sub I of tau, w sub I of tau prime, acting on phi of minus infinity. And this is the second order correction. Now it turns out that to an arbitrary order, so we can express the with n tending to infinity. So then we have the solution phi of t equal to some object that is called the scattering matrix T of s of t comma minus infinity times phi of minus infinity. This object, what it does is that it evolves the state from minus infinity to t. So that's actually pretty clear from the notation. And then and the scattering matrix contains all the terms to infinite order that contribute to the correction of phi of minus infinity. That contribute to the correction of the quantum state from phi of minus infinity. So then this scattering matrix is nothing but the summation from n equal to 0 plus infinity of 1 over n factorial I over h bar to the power of n, succession of integrals minus infinity to t dt1 minus infinity to t dt2 minus infinity to t dtn, and you should just keep on going. Now this, of course, n tends to infinity, and this is the time order product of w sub I of t1 times w sub I of t2 times w sub I of tn. This is for n, of course, from 0 to infinity. And then this is how the scattering matrix is defined. And since this is a time order product here, and we have the factorial and the summation and stuff like that, so we can express this as the time order product of the exponential of minus I to the h, minus exponential of minus I over h bar, integral from minus infinity to t of w sub I of tau d tau. Okay, but this is the scattering matrix, and now you can see that for n equal to 2 in this case, you will just get back what we have for the second order correction of the quantum state here. And even though we're not going to use all of this in linear response theory, we're going to use only up to first order, which means that we're only going to use the first order correction in linear response theory, as its name says, which is 1 plus 1 over I h bar, integral from minus infinity to t of w sub I of tau d tau, all of it acting on phi of minus infinity. So I consider that it was, let's say, a good review to actually just talk about this scattering matrix and to see how to construct approximations to the quantum state to an arbitrary order. So then at the next opportunity I will show you how to construct the approximation to order 3, and next I will develop the formalism for the Kubo formula in terms of group functions. Thank you for watching.